my friend from Imperial College, who's going to tell us about stochastic Euler-Boussinesq convective adjustment. Okay, Darryl, and you have about 50 minutes, 55 plus 5 minutes for questions. Thank you very much.
Well, I advertise this talk as Rayleigh-B enard because, you know, this is what Charlie was interested in so much, and I wanted to learn something more about it. And one of the things I learned is that since I'm interested in the initial value problem, and I want to use Hamiltonian methods and Hamilton's principal methods, so I don't have any viscosity or any diffusivity, that I can't have the boundary conditions that are in the Rayleigh-B enard problem. So I have to do the Euler-Boussinesq convective adjustment. Okay, so so that corresponds to the Rayleigh-B enard problem, in which you start as an initial value problem, and the temperature, you let the temperature go to be whatever it is, and the temperature can then depend on the horizontal component in a coordinate on the upper and lower boundary. So that's why we changed the title. I'm thinking a lot about Charlie. Thank you very much for organizing it, Dries and John, the others. Yeah. Yeah, I remember Charlie very, very well. And he had this thing he called or maybe other people too, called it its obsession for convection. One of the things I did, just to check, if you look, you'll see in Google Scholar, if you just search on Doring and not obsession, not on convection, you see like thousands of hits, and it's remarkable. Yeah, Charlie had a big effect on this field, and so I'm gonna talk about something that I started thinking about, you know, because of this talk. So let's see, how do I change? Sorry. Okay, scrolls. So this can so that was Kate and Will going home to the palace. Okay, so this topic is relevant to what I'm working on now, and this project is called the STUOT. It's a synergy project from the European Research Council, called STUOT stands for Stochastic Transport in Upper Ocean Dynamics. Okay, and if you want to know more about it, you can look at that website. It involves 3 institutions: Imperial College, IMRIA, which is in the French National Computational Science Center, and EPHEMER, which is the French National Satellite Oceanography and other types of oceanography as well, and they're connected to the European Space Center. So I'm getting inundated with models of data now, and so that's part of the background of what I'm talking about. Okay, so here the challenge is we need stochastic parameterizations of fluid convection in models that are needed for data analysis and data assimilation. That's what STUOT is about. And so the question is, well, the question is, ask not what math can do for oceanography, but ask rather, what can oceanography do for math? And so the question is how to derive stochastic parameterizations that preserve the mathematical structure of fluid dynamics. So the approach that we'll talk about today is the introduction of stochastic constraints into Hamilton's variational principle for fluids. Okay, and I'm going to take one line of thought that goes through 3 famous contributions in the turbulence theory and in stochastic mathematics. The first one is the Craignon model, which was about the Stochanovich stochastic passive scalar transport, and has been, had an enormous effect on how people think about the statistics of turbulence and the statistical physics of turbulence. Then it's Landau-Lifshitz model of fluctuating hydrodynamics, which you think of not as transport. It's not stochastic transport, it's stochastic forcing, by the fluctuations. And last week, Greg Eink talked about this model and its effect on turbulence when you're very, very near equilibrium at very, very small scales. And last I'm going to talk about McKean's, Henry McKean's contribution, and by making an adjustment to the stochastic equation, introducing the mean field, you can compute how the covariances of the fluctuations are affected by the statistical correlations in the fluctuating dynamics. Okay, so this is the basis, and this is why the talk has 3 parts: for Craignon, Landau-Lifshitz, and McKean. Okay, so if we start with Hamilton's principle, and we ask for structure preserving fluid approximations, Hamilton's principle, first of all, we have a symmetry. So we're using always reduction by symmetry of Hamilton's principle. And the symmetry is the relabeling of the Lagrangian labels for the Eulerian coordinates. So Eulerian coordinates don't depend on Lagrangian labels. The effective quantities do, but not the Eulerian velocity, for example. And the first thing that gives you is a thing called the Kelvin-Noether theorem, which gives you a circulation theorem and gives you, for example, in the case of GFD, it gives you the conserved potential vorticity. Now, the feature about the Hamilton's principle is you can make your approximations in the Lagrangian in Hamilton's principle. You can do asymptotics, you can do Lagrangian averaging, you do Hodge decomposition. And each time you start making these approximations and introducing asymptotics, for example, when you do Hodge decomposition, then you get another set of models, which in fact is, since it has come from Hamilton's principle, will have a Kelvin theorem, and the Noether theorem will give you constants of motion. And the other feature you have when you're modeling in Hamilton's principle is the Legendre transform. And the Legendre transform will take you over to the Hamiltonian formulation, but it won't be symplectic. It'll be something that's associated with variables that are invariant under this reduction by symmetry. And they'll be in the Eulerian form. They won't be Lagrangian dynamics, they'll be Eulerian dynamics. We'll have the Eulerian conservation laws. The critical points of the sums of the conservation laws in the Hamiltonian will give us relative equilibria. These are equilibria with motion, and that can lead to methods of studying nonlinear stability. Okay, so that's why I'm doing this. When you do this, when you take one of these directions away from the fundamental equations, you can get a whole network or a tree. For example, here's a tree of GFD approximations in 3D, 2D, 1D, starting with the 3D Euler equations for stratified, rotating, incompressible flows. If you assume small buoyancy stratification, you go to the 3D Euler-Boussinesq equations for stratified, rotating, and compressible flows. In our case, we're going to go actually to 2D and not be rotating, but we're going to have a 2D vertical plane, not a horizontal plane. All these other models like to see things in horizontal planes. Okay, but this is just an example of how you can diagram what happens when you start making approximations in the Lagrangian and Hamilton's principle. Okay, so we're going to discuss the single stream of thought. We're going to link these ideas for stochasticity, from Craiknon, Landau-Lifshitz to McKean. Okay, for Craiknon, what we're going to do is we're going to make the Hamilton's principle stochastic. And we'll follow Craiknon in this. We'll constrain the variations in the reduced Hamilton's principle so that the Lagrangian paths or the Lagrangian histories are stochastic, and stochastic in the Stratonovich sense. The reason we want to be a Stratonovich is because Stratonovich has a product rule and a chain rule. And so you can take variations in this, just using ordinary calculus in Hamilton's principle if you have Stratonovich stochasticity. Now, the next step was, this is like the step that we're hearing from Greg last week about how the Navier-Stokes equations, which Craiknon was working so much on, well, wrong. The way he was trying to explain it was in terms of these forces, or stochastic forces that had to be included into the Navier-Stokes equations, for example. And to get those, what you do is you constrain the variations in the reduced Hamilton's principle using the thing called the Lagrange-D'Alembert approach. That approach allows you to bring in, you constrain the variations so that the force that you're trying to add doesn't do any work. And finally, now to derive the expected dynamics, or the dynamics of the expectation quantities and covariances and statistics, tensor variances, we follow McKean. Henry McKean introduced the idea of this mean field plus stochastic fluctuations in a fundamental mathematical way, and it fits into this whole framework. We take the variation and then we follow McKean. Okay, this is what we're doing. So we're going to just talk about one example, which is vertical plane Euler-Boussinesq convection equations, EBC. And here's what they look like in the velocity and temperature representation. The velocity is u, the temperature is theta, and the velocity is divergence free. Okay, and if we think about vorticity and temperature representation, we take the curl and that temperature part, and we absorb the various coefficients or units into that term in theta. Then we have this simple equation here. If the theta wasn't there, it would just be Euler's equation. When theta is there, then variations are the horizontal derivatives and the temperature theta drive the vorticity. The vorticity in turn drags the temperature, and they do a little waltz together. And you'll see some examples of this waltz. Now, so you think of it, now we introduce the stream function, and these have a peculiar representation of the XZ plane if you want to have a right-hand coordinate system, but this is how it looks. And the vorticity is plus the Laplacian of psi in the right-handed coordinate system. The boundary conditions are that the velocity is tangential to the upper and lower walls as z equals 0 and 1 is periodic in the horizontal direction with coordinate x. Okay, so then we'll talk about this vorticity and temperature representation in terms of Jacobian. Okay, so if the Jacobian comes naturally into the transport term, and then the Euler-Boussinesq equations become just all written in Jacobian form. The Jacobian form tells you you're doing something very geometrical. I mentioned we have a Kelvin's theorem. So the Kelvin circulation theorem for the EBC, the Euler-Boussinesq convection, is time rate of change of the circulation of the integration of an Eulerian velocity, u dot dx, following a Lagrangian loop, a material loop. So that velocity in the loop is the transport velocity, and this velocity in the integrand is the momentum per unit mass in an inertial frame. so it's Eulerian. If we do Stokes on this, then it's the time derivative of our integral can be written in terms of the Stokes on the Jacobian. So yeah, this means that if z and theta depend on each other, their gradients will be aligned. And if their gradients are not aligned, then this term is going to generate the vorticity. Okay, so let's look at some simulations of this initial value problem. Okay. So these simulations were done by Pan, and this is the vorticity, and this is temperature. The one on the left is the vorticity, the one on the right is the temperature. And if you start with, always you think of a hyperbolic tangent running from the bottom to the top. Yes?
Stop seeing the simulation. We don't see them.
Ah. Oh.
Last picture, we see Kelvin circulation theorem for EBC.
Yeah, okay, so I switched to another, maybe I have to.
Maybe you should stop sharing and then share again the whatever you need to show simulations.
Different frame, yeah, okay. Good, thank you. Thank you, Idris. How about this? Are these beautiful? Can you see them? Tell me when you can see it.
Yes, we do.
Okay, so on the left is the vorticity, which started out in being, a 2x2 patch of sines and cosines. And on the right is the velocity, where the warm colors are warm and the cold colors are cold. And it starts out with, in gravity is pushing down, and it starts out being all warm on the above with the hyperbolic tangent, and then cooler down below with again, the rest of the hyperbolic tangent. So that's always going to be the way we start the temperature. But the first time we started at the vorticity, we started with a little activity. You can sort of see that it has a sine, cosine, sine thing. Okay, and oops. And so a little bit later, then you see there's some development, and these this view, the sort of symmetric view starts still symmetric, but it now has much more activity in it. And you can see that the vorticity is dragging things around, and the temperature is replying to it. And so let's just take another look where we start with the case where the vorticity is 0, so fluid's at rest, and we start with the hyperbolic tangent profile for the temperature again, and we'll let it go. And it's, of course, it's the cold water above the warm water, and so it starts flowing. So we're getting a plume in the and so the and with that plume now is turning, has derivatives in the x direction and the direction, and that's also turning on the vorticity. Okay, and things become more intricate, and you can see that there will be other simulations with higher resolution that resolve the high wave number things that are beginning to develop. So this is from rest, hyperbolic tangent form of the temperature and from rest. And then this last one, what we do is we put up here, right, just a little bit off center to break the symmetry. We put a little Gaussian shape of vorticity and let it start swirling, okay? And so it develops into, some shape here in vorticity and pulls the heat downward, and that forms this shape, right? Has some hotspots of vorticity to it, and and some stretching. And if we try the same experiment with the vorticity downstairs, you more or less get the flip of it, except that the temperature things. Okay, Okay, so that's this is what the solutions, the inertial value problem that we're looking at, you know, what it looks like. And you can think of this as data as you want. You can think of, say, this is data, this is
There's a question here, Darryl.
data. Yeah, tell me.
It seems to me that in a lot of them, the hot is above and the cold is below.
Yeah, I know. These are, this
Are
is,
they upside down, these things? No,
they could be. They could be. This is hot off the press. It just, you know, we just got it last night.
especially the plume.
Yeah. I look okay. So it looked like this plume.
Idris is saying no.
No heating and cooling. The model does not take into account that there is heating.
But that one there, that
Yeah.
looks.
But the original model, there is no heating or cooling from the boundary. By the model.
No, I believe that.
Yeah. So to me, right now, I've only seen these today. So I don't know whether the color is exactly right. So I'm not going to make a claim. Okay. I'm sorry about that.
No problem. No problem.
Okay. So then I'm going back to the PDF. Let me share again. I'm getting so good at this. Can you see the can you see the PDF? You see the slide yet?
Yes, yes, we can see it.
Thank you. Okay, so we saw the wave pan figures. Now we're going to talk about conservation laws for ABC. Okay, so the concept, you know, the ABC dynamics preserves this integrated energy. Okay, here this is what the integrated energy looks like. It's kinetic energy plus potential energy. And when gravity is around, there's this minus sign. But it turns out that you can write this as a sum of squares and then subtract something which is just a constant and doesn't affect the time rate of change of the energy. The z squared, of course, doesn't. But the interesting thing is theta squared doesn't either, because the integral of theta squared is also preserved. And it's preserved because there's a whole family of integral quantities called Casimirs, which, for example, an arbitrary function of theta will be preserved. Oh yeah, that's because theta is just being advected. So we can't do anything except move things around. And so it's, you know, even if it's a nonlinear function of theta, it just gets moved around. And the advection equation for divergence-free velocity tells you that's going to be conserved. And the interplay between the two gives you another conservation of any other function of theta times the vorticity. Okay, so these two are hallmarks of the deterministic equations for ABC. Either, you know, so the Casimirs are conserved, and the Casimirs go with the circulation theorem. And there's also the energy, which is conserved. Okay, I'm mentioning this because we're going to look at, you know, first of all, what makes the energy get conserved. The energy gets conserved because the equations can be written in this Hamiltonian form here, in terms of an antisymmetric operator acting on the variational derivatives of the energy with respect to the vorticity, but that gives the stream function, and with respect to the temperature, that gives the temperature minus the coordinate z. Okay, and that defines a Poisson bracket in terms of this operator here, J. And for any Hamiltonian, not just H sub ABC, for any Hamiltonian, we find out that the Casimirs are conserved, and that's because the variational derivative of the Casimirs turns out to be in the null vector of this operator, this matrix operator. So it doesn't matter what that what Hamiltonian you choose is. In particular, this is our opportunity. we can preserve this Hamiltonian structure. We can preserve these conservation laws, an infinite number of these conservation laws, if in fact we say the Hamiltonian should be semi-martingale. So we can introduce noise into Hamiltonian system. It's still Hamiltonian and it still describes motion on the level sets of these Casimirs, but now it's stochastic. Okay, so this is the stochastic advection by Lie transport. And the Lie transport shows up when you take the variational derivative of the semi-martingale Hamiltonian. You get the stream function as before, plus you get a whole sum of transport vector, the whole sum of stream functions, each of which has their own Brownian motion, and each of which has some shape which corresponds to something like normal modes of the noise, and which is something that we have to derive from the data. When you look at the coarse scale data and try to compare it with fine scale or try to assimilate data that's being measured, that's how we're going to be able to find out what these guys are. Generally, for those who know about this data assimilation, one way of thinking about them is EOFs. Another way of thinking about them is eigenvectors of the velocity correlation function. That is not these guys, these are the stream functions for that. In fact, the vector, there's that Poisson bracket. Okay. Oh yeah, I made a mistake. This should be D. This should be that D there. That D is the stochastic time differential corresponding to a Stochanovich integral. Maybe it's like, here's what the vector form of it looks like. It's that D. D is a stochastic differential for a Stochanovich integral in time. And here's how the equations look in terms of the velocity. For the vorticity. Okay, so the transport, now this is transport. And this is what I mean by following Craignon. The transport velocity has become a semi-martingale. And the histories of the Lagrangian parcels will be following the characteristic curves of this vector field here. The one that's advecting the theta, that's an advective quantity. This is then if we were to put this diffusivity in there for the theta equation, and if we were to say, well, we're only going to talk about some set of constants, just one Brownian motion. That's the Craignon model. Okay, and the famous Craignon model. And now what the variational principle has done is coupled it also to the vorticity motion. Okay, but it's the same transport velocity. Okay, just then this is the one which also conserves all those Casimirs. Boundary conditions are the same as before, and the noise terms have to be compatible with those boundary conditions. So here's a question. Do the salt EBC equations have a stochastic Kelvin theorem? We should take a vote maybe, but I think we're running out of time for that. So yeah, they do. In fact, the salt EBC equations emerge in Kelvin form. Okay, so here, this velocity is grad perp on psi. That's the velocity corresponding to the, it's called the drift velocity in the transport vector field, but it's also the velocity corresponding to the momentum per unit mass. It's in the integrand of the Kelvin theorem. And so the noise appears in the loop, and the loop is material. The loop is a loop of fluid parcels, which is moving around. It's moving around with the stochastic vector field. It's stochastic in time, okay, but it's sufficiently smooth in space to generate a smooth invertible map for its characteristic curves. And that means that the loop will not come apart like a smoke ring. The loop will stay together. It'll stay as a material loop. And this D actually, amazingly, satisfies the chain rule. And you can calculate the evolution equation and prove that this is the integral of the evolution equation in the inertial frame. And that's the Kelvin form of stochastic. This stochastic in the sense of stochastic advection by Lie transport. It's just transport by this vector field. Okay, and the right-hand side doesn't change. This stochastic, integral has changed, but the integrand of it hasn't changed. Okay, so this is what it's a slight extension of what Craignon was saying many, many years ago. This is the Craignon. Here's when in this paper, Craignon started talking about stochastic Lagrangian histories. In this paper, he introduced the Craignon model for thinking about statistics of turbulence. So what next? Oh boy, yeah. I'm surprised you didn't ask me about those C's. We need the C's in order to close this model. So here's how we get them. Let's call it the SALT procedure. So it's involving, we're gonna, for simulations, you can think of it as involving 3 levels of description. So the top level would be the fine scale truths, the heroic calculation that tells you, for example, for the Euler equations, it tells you the result, like I saw those simulations for very high resolution. That's the truth, but it's not affordable all the time. So, the second level is the coarse scale version. Okay, that's where the SALT stochastic PDE comes in for this 2D Euler velocity. Here's the Euler equations written this way. And it might surprise you, actually. The Euler equation has this other term there. That's the term that gives you the Kelvin term for the stochastic theory. This is the transport velocity. And now what you have to do is make some kind of comparison, say by projection, and then some calculations. There's a sequence of calculations you need to do to find coarse-grained this thing, and then find the displacement from the truth. And this will tell you the EUFs of that displacement will tell you the C's. And you can choose to stop. Okay, you can stop at some level, and when you stop, you'll be able to quantify the uncertainty of having calculated at the coarse scale something that you knew at the fine scale. On the other hand, there's a data assimilation step, which allows you to, even at much coarser scale, just put some data that you measured, which is also the data, and carried by the fine scale. A little bit of this data will drastically reduce the uncertainty. It just crashes the width of the ensemble down around the truth. Okay, so the SALT procedure then follows the steps. You begin by implementing some PDE on a fine scale, say the Euler equations. You obtain its correlation statistics. Okay, these are the EOFs and the C's at the coarse scale. And then you create a database, right, of these Lagrangian tracers from the fine scale. You calibrate the Eulerian eigenvectors. This is how you estimate them. And maybe in later we hope for the STUART program from satellite data. And from this you derive the SALT stochastic PDEs with this drift and noise velocity. And then you simulate them to quantify the uncertainty, and then you do the data assimilation to reduce the uncertainty. That's what this STUART program is about. Okay, now what about forcing? Stochastic forcing by lead transport is what we call the method that you get from this Lagrange-Delibert approach. I'm not going to talk about that so much, but the point is, this is an idea of Rio who is my PhD student right now. There was some question about how could you make the stochastic flow preserve the energy. And he said, well, look, this J function here, this J operator is skew symmetric. The energy, the original energy will be preserved and it'll be stochastic if in fact the Poisson bracket was stochastic. And here it is, that's what you get from that. And then that turns out to be something that you can put in directly from you can put this thing in directly from the Lagrange-Delibert method. It's then it becomes very flexible. Now, here's what happens is that this stochastic forcing EBC preserves the deterministic energy, but not the Casimirs, and doesn't have it doesn't have a Kelvin theorem that's with a stochastic velocity. The salt version of EBC preserves the Casimirs, but not the energy. The energy is a semi-martingale, depends directly on time. And if you compare this fleet process of data assimilation with the salt one for the 3D primitive equations, which is treated on another student, Stuart Patching, for his PhD thesis, but there's a new paper out right now about by Hu and Patching, which talks about how you compare the slate and the salt methods for the 3D primitive equations. Okay, so now let's finally talk about the EBC climate in the sense of the equations for the expectation. Okay, now for this we take an idea from McKean, and we split in the LA salt EBCA system. We keep the same Poisson bracket again, okay, the one that we had for salt, and that's also the deterministic Poisson bracket. That's the Poisson operator. And then we do what McKean said. Suppose you use the mean field for the drift, and you keep the stochastic process you had from before. Okay, then, well, what do you get? What do you have from that? I mean, you can't very well just say, oh, I'm going to know what the solution for the expectation was by the stochastic PDE. You have to somehow get it. But first of all, it still preserves that whole Casimir family again. So you have that really lowers the dimension to be on for having an infinite number of conservation laws. It also has a Kelvin theorem for that matter. In vector field, it looks like in vector form, it looks like this. So the expectation is appearing in the drift, okay, of the vorticity and temperature equations. And the derivatives of the expectation of the stream function is what comes into the vorticity description in terms of the Jacobians. And these C's now go back to looking at their stream functions. Boundary conditions are the same as before. And as before, the noise terms should be compatible with those. How you make that happen? How do you get C's that are compatible with that? Well, that's part of the constraints. They have to be constrained. Okay, so let's look at the Ito form of those Stratonovich equations. There's the Ito form. You can't look at the expectation until you get to the Ito form. So in the Ito form of these equations, looks like this. This is the Ito correction going from Stratonovich to Ito, and it is a second order operator. And if the C's are divergence free. You can put this thing on the outside. That's the divergence of a symmetric tensor contracted with the gradient. So it's just, morally speaking, this is Laplacian weighted by CC transpose. And it looks, well, it looks like the viscosity, and it requires an additional, and it requires an additional boundary condition to, you know, to solve for the expectation. You know, I don't know quite how to get around that, but I can get around it if it's periodic, for example. So now we have the expectation here. We have the Brownian motion here. Okay, just Ito Brownian motion. Everything over here is linear. It's, you know, linear omega. C's are given. Theta is linear. Everything else is linear. And we can take the expectation. So if we take the expectation, the Brownian term will go out. Okay, that's why we did Ito. And here are the equations for the expectation. And now we can get the thing we need, which is the expectation of U. So these equations are parabolic in a sense. They're just like the, you know, Oberbeck equations, or Oberbeck something equations that for RBC, for the Rayleigh-B enard convection. But like I said, the boundary conditions don't make it the Rayleigh-B enard problem. Still, we can, for this problem with these boundary conditions, we can compute the expectations of the solutions. And then we can take the difference of the solution from its expectation to define the fluctuations. And the equation for the fluctuations is stochastic, but it is linear in the fluctuation quantities. Okay, so the equation has this expectation. These equations govern the fluctuations, and they're linear. And if they're linear, then we can calculate their covariances, and we can try to figure out if we could actually get the dynamics of the covariances. Well, everything is looking good here. This is for the vorticity covariance, and this is for the temperature covariance. And you ask for the equations, just do the product rule on the Ito formula, and take the expectation, and we get these equations. This one here, everything, this one, that one there, right? This is the form that you get. See, both of these have the same form. In this one here, this one we know everything except this one here. We don't know the expectation of the cross correlation. Okay. On the other hand, the cross correlation is obeys a PDE also, and so this is a PDE for the cross correlation, and well, cross correlation. Now this one has the same form as the other guys on the right hand side, but that one produces the expectation of the covariance of the derivative of the temperature, but that term actually has an equation too. So this means we can calculate the covariance dynamics for the LA salt Euler-Boussinesq convection. So we've done the thing. We have got salt by using Craigno's idea. We got Sleet by using the Landau-Lifshitz fluctuation idea. And now we also have LA salt by using Henry McCain's idea. And for this case, this is a basic case. Things can be much more complicated, but this also just happened to work. So in terms of conclusions, let me say something about the current status and open problems for this. First of all, the local existence uniqueness well-posedness weak solutions for the stochastic Euler-Boussinesq convection and blow-up in its blow-up criteria. These have all been proven by Diego Alonso Aran and Anthony Betancourt de Leon in a paper in JNLS in 2020. And then for the expectation equations, these have global strong solutions for the LA salt PDEs. And this is in a paper again with those guys and some other guys. Then this application of the work for this model and data assimilation is a work in progress, but some of it has been accomplished, and this method. Yeah, I don't see any reason why this method is not going to work for the salt procedure. And almost finally, the salt approach has been generalized to geometric rough paths recently in a paper which is about to appear in the Advances in Mathematics. The geometric rough paths have the thing that the Stratanovich noise has, is they have something which allows the variational principle to be applied. They have product rule and chain rule. And the chain rule is what you need to get the Kelvin theorem. And when you get that, you get this Lie derivative thing from the Kelvin, and when you're use the chain rule in the Kelvin theorem. And that Lie derivative idea is fundamental to this stochastic advection by Lie transport. Okay, so thank you very much. Thanks for listening.
Thank you, Darryl. Are there any questions from the audience? Okay, no. Are there anybody in the questions or comments? Okay, I have a question, Darryl. Can you go please to the discussion last? Yeah, you mentioned here, I'm trying to understand the item 2, proof of global strong solution for LA slat. I mean, I cannot follow all the increments, increments that you have here. This is maybe inherited from Los Alamos.
This one here.
They are famous for these kind of acronyms. Yes. Yeah. So can you tell me this result about global existence? I mean, for which model? And
it's only for this. It's only for this right here. Only for those two equations. So
everything is expected. I mean, like everything is so I can.
It's not at all stochastic. It's a PDE.
It's a PDE. So, but so the PDE is the unknowns is like the primes, or what's the unknowns? The unknowns are the omegas.
The unknowns are these E of omega and E of theta. Okay, so these are deterministic functions. So everything with an E is a deterministic function, and what you need is for taking this divergence to be a positive definite operator.
So this basically, this positive definite operator sort of like code-to-code viscosity on E omega and diffusion on E theta.
That's right.
Okay, all right. Then that's fine. So this is like 2D diffusion Bénard whatever. Okay, then not surprised. Thank you. That's what I wanted to say.
It's not a surprise, but it's it's
no, I mean, said no.
It's a bonus.
No, that's perfect. No, I said, I mean, the global result for Invisid was surprise to me, but when I saw the diffusion coming from this stochastic process, then it's okay. I mean, like it's correct. That's fine. I mean, like.
You get the C's from data, and if the C's don't give you a positive definite operator, you should go look for more C's.
No, I understand. Yeah. So, no, I understood that basically you have an extra diffusion coming from the process. That's what I was missing.
That's right.
Other questions or comments? Yes. No, I asked. We have a moderator here, Xen. There's nobody on the Zoom, yeah? Oh, yeah, there's a question here.
Hi, Darryl. This is Greg Cheney. I just wondered. coming back-
Hey,
Nice to see
hi.
you. Just understanding, the original framework, since it's based on Euler, you can't have boundary forcing. And perhaps this is a
Right,
naive
that's right,
question,
that's right,
but the
that's right.
equations that I'm staring at right here for the expectations, because they have this diffusive-like term for which you said you might need some boundary conditions.
Yeah,
Can that be a virtue? I mean, does that mean you could somehow treat boundary forcing?
well, here's the thing. We thought we could start out with those initial conditions that I explained, right?
Yes.
And we could hold the temperature at 0 on one side and 1 at the other side.
Yeah.
And then require that the temperature is constant,
Uh-huh.
okay, on the upper and lower boundary. But in order for that, then we need something also about the derivative.
Right.
We need an additional boundary
Sure.
conditions about the derivative of the temperature. We could, the problem is we just wouldn't run. We couldn't get it to run on a finite element code.
Yeah. Okay.
Okay.
Thank you.
Yeah, and you could see in the simulations that the temperature does not want to be constant on the upper and lower boundary.
No, but that's because of the equation, where you had just the temperature be constant at a material point, and they never cross the boundary, so there should be no
No,
boundary.
that's right, but the x derivative is not 0. Okay. Yeah, that's right, but yeah.
But
The code doesn't know about that. You're saying that if the value of, that's what I was saying too. But if say, look, the point on the boundary stays on the boundary, right? And it carries the temperature. Okay, but I don't know, it wouldn't work on the code at all. When we change it to let the temperature be variable on the boundary, we got those simulations just in time for this talk.
Okay.
Darryl, okay, there is a question here. 1 second.
No, thank you. Darryl, you mentioned this paper about where you use rough math. So which model you solved by using rough math, and what precisely is the result?
Okay, 3D Euler. So basically all the results that you can get for the deterministic problem have their corresponding result for rough paths and the salt type of rough paths with periodic boundary conditions. So periodic boundary conditions with 0 mean, so that you have the Biot-Savart law. And if the vorticity starts in W22, then you have local weak solutions.
Okay, thank you.
Who was asking the question?
It's this one, Brzeźnia.
Oh yeah, it's Ziswa. So Ziswa, do you think you can? Do you think that's sensible? Do you think those are, because I think it's online at the archive if you want to take a look. Ziswa, I cannot hear you.
Oh, because I took the microphone from him.
Oh, that's bad, isn't it?
So what paper is it? With whom did you write it?
With Dan Christen and James Michael Leahy and Nilsen Torstein.
Okay, I'll have a look. Thank you.
Yeah, thanks a lot for your question. We are really proud of this result. It took 2.5 years to get a referee report.
Okay, well, okay. Other questions or comments? Well, in that case, thank you very much, Darryl, for the talk, and hope to see you sometime soon in person. Thank you.
Okay, thank you, Idris. Okay. Bye-bye.
All right.